In this video, we are going to look at the question of how the electric potential behaves in a uniform electric field. We know that the uniform electric field is a very simple field to deal with mathematically. It's one of the simplest fields you can have. And it turns out that the electric potential also has a really simple relationship, and it changes in a very simple way in this type of field. So let's just start off by remembering that if you have a uniform electric field, let's say one that goes from left to right, that means that when you place a charge in that field, no matter where you place that charge, it's always going to feel exactly the same force. And that force can be calculated by multiplying the charge times the value of the electric field. So wherever I put this charge, it's always going to be pushed to the right, and it's always going to be pushed by the exact same force given by this formula. So we have to remember that and keep that in mind. So now let's look at the picture here, which shows a uniform field which is directed down. And so all the field lines are pointing from the positive plate down towards the negative plate. And we're going to look at what happens if we allow a positive charge to move with the electric field. That is, to move in the direction of the electric field. So I'm going to allow this charge to undergo a displacement in that direction. And as the charge is moving in that direction, the electric field is also going to be acting on it by pushing it that way. And so what we want to think about is, in this situation, when a positive charge moves in the direction of the field, first of all, what type of work is done by the field? Second of all, what's the change in potential energy for the charge? And most importantly for us now, what is the potential doing? How does the potential change? So let's go and address those questions one by one. First of all, the work done by the electric field is positive because the force and the displacement are in the same direction. And then we can say that the amount of work is equal to QE for the force multiplied by D for the displacement. So the electric field is doing this amount of work, positive Q times E times D. Now, the result of that positive work is going to mean that the potential energy of this charge is going to decrease because the field is pushing it in the way it wants it to go. And we know that the change in the energy is equal to the negative of the work that's done by the field. So remember that. And therefore, the work that's done in this case would be negative QED. This is always going to be true for conservative forces. Whatever work the field does will cause an opposite change in potential energy. And so lastly, we come to the idea of how does the electric potential change. But electric potential is just defined as energy divided by charge. And so all we're going to do here is divide out this Q. And so we end up with dividing Q, and we find that the electric potential decreases by E times D. So the change in potential going from this point to this point is going to be a decrease. And it's a decrease because the actual potential energy is also decreasing. So these two things have to both have the same sign, because they're both decreasing in this situation. Okay. This relationship is actually a very simple one because it tells you that as you move down or with the electric field, that the change in the potential, the change in V, the voltage, is going to happen in a very linear, nice sort of a way, in nice linear steps. And so if I start, for example, at this point, which is at 100 volts, and I move down, I'm going to find I might drop down, I don't know, to 80 volts. But if I move another distance, which is exactly the same distance, I should be down to 60 volts. And this continues. And so if I'm taking nice steps, right, equal to D, my change in potential is I'll always be losing 20 volts with each step. And that's because the change in potential is proportional to the distance. So this is actually pretty nice, that it takes these nice steps. You can also look at this, we'll do one more case here. What if you look at this from the point of view of a positive charge which moves opposite the electric field? So it has a displacement which goes up. We would, first of all, have to remember that the force is still going to be going down. And in this situation, because the force and the displacement are opposite, the work is negative. Now, the charge won't naturally move upwards, will it? But you could move it, an outside force could move it upwards, or you could like shoot it out of a gun or something and have it travel upwards, and this force would act in the opposite direction, much like if you threw a baseball straight up into the air. Okay. So in that situation, the work is negative. That would be a positive change in energy. So the potential energy increases as this charge goes up against the field. And the change in potential would now be positive ED because we're dividing out the Q. So in this situation, as you go up, you find out that the change in potential is positive ED. Sometimes people talk about ED. There's ED. And ED's really important for understanding uniform electric fields and how the potential changes. By the way, if the charge goes this way, if the displacement goes that way in the field, then the change in potential is 0. So that's a little aside there. That's very important. So you don't get a change in potential when the charge moves perpendicular to the field. So a conclusion here would be that traveling in same direction of E causes potential to decrease. Okay. And kind of the vice versa is also true, that traveling in the opposite direction of E causes the potential to increase. So I'm going to save on my ink here. And that change in potential, my delta V is going to be either plus ED or it's going to be minus ED, depending on which way I'm going. All right, well, that's a big deal. One little side note I'm going to say here is, now that we've talked about that, you might be wondering if there's any such thing as a gravitational potential. And the answer is yes, but it doesn't get used very much. I'm just going to say that if you think about this, if you have an object of a mass m and it falls a height h, the work done on it is going to be equal to m times g times h. So instead of QED, now we have mgh. And that's positive. That means the change in energy is going to be negative mgh. And we could kind of think about gravitational defining gravitational potential by dividing the potential energy by mass instead of charge, because this is gravity, right? And if you do that, you would end up with this negative g times h. So the long story short is you could actually define kind of a change in gravitational potential, and it would just be g times h. And that's kind of like negative E times d, isn't it? But it's not really used much. It's not used at all. And the reason is it's easy to measure g, so we don't need to kind of worry about that. Remember, with electricity, it's hard to measure E. And so we have to use voltage instead, because voltage is easy to measure. So anyway, there is gravitational potential, but it just doesn't get used because it's not really useful from a practical point of view. All right, let's end here with two examples that will help you to understand stuff in problem solving. In this first example, it says the voltage difference across the plates shown is 300 volts. So from here to here is 300 volts. The plates themselves are 0.03 meters apart. So that's the total distance. Now I'm going to divide that distance into 3 pieces. So if the total distance is 0.03, then if I split it into 3 pieces, well, each of these pieces will be 0.01. And so then what you do next is say you're asked to find the electric field strength and determine what the voltages are at these different points. So the first thing you do in a case like this is find electric field. And you can get that from the relationship that we just figured out, that the change in voltage is equal to ED. Now you solve for E. And then we take our change in voltage, which is 300 volts, and we're going to divide by the entire distance, which is 0.03 meters. And when you do the math on that, you get 10,000 volts per meter. And so the electric field is a nice constant value of 10,000 volts per meter. Right? This is uniform, so it's always that much. You might be wondering, hey, those are different units. We've never talked about volts per meter. But I will tell you that volts per meter are the exact same as newtons per coulomb. And so for now, you can just take my word on that, and we can kind of show that later. But they're equivalent to each other. All right, so you've got a pretty strong electric field. Now we want to figure out how does the voltage change, and that's not too bad to figure out. If you say that the voltage at A is 0 volts, and you think, well, how can I get up to 300 volts by the other side? All you do is you just divide 300 into 3 equal pieces. And so that would be 100 volts here, 200 volts here, and so on. And it's literally that easy. So if this first plate is at 0 volts, then you know that the other voltages will be just 100, 200, and 300. Okay. You might be wondering, well, how do you make that plate 0 volts? We can talk about this later, but you can ground this electrically to make it 0 volts, and that forces the other plate to be at 300 volts. You could also do other things, okay, and this is just to throw this out there. It is possible that this plate might be at 500 volts. Yeah, I mean, for now, just imagine you could connect this to a 500 volt wire, and so now you've got 500 volts a day. And the question is what happens when you go across? Well, when you go across, you've got to go up by 300.